Ooh, there we go. All right, we're all set. All right, well, thank you all for coming out. At least somebody showed up around here. So I'm going to see what I'm doing here. So this is a lecture I've been giving pretty much every year for the last 5 years. But this is the first time I've actually updated it a little bit, so you guys are lucky to get some of that information. Let's see. Is it going to advance? There it goes. I got it. So just a little about myself. I got my PhD in electrical engineering here at the University of Utah. And could we also bring this image down? Supershish? Is there a way to bring the projection down? Maybe
I don't think so.
crank that? Is that just that?
No,
Okay.
I guess, yeah, that's fixed.
Oh, all right. Well, we'll flip with it then. So right now I work for the Department of Metallurgical Engineering. I do a bunch of research in metal sorting and electrodynamics and eddy current theory. So I'm just kind of showing off here my little picture of magnetic field and a magnetized bar, because I just figured that out a couple weeks ago and it looks cool. So that's the sort of thing I've spent a lot of time on, just modeling physics and solving Maxwell's equations and all that good stuff. So today's topic, we're going to be talking about light trapping, what it means, the applications are, and specifically we'll be focusing on how it relates to solar energy. That's basically what I did my PhD dissertation with. So what is light trapping? Just kind of the basic philosophical foundation is you just imagine an object somewhere in space. There's a bunch of light striking it, and some of that energy is going to bounce away, some of it might transmit through, and some fraction of that's going to be absorbed inside of your thingy. So we can define just a basic metric called light trapping efficiency, or call it absorption factor as well, which is just the ratio of all the energy absorbed inside of it divided by all the energy that was striking. So it's pretty straightforward. So what are some basic applications for light trapping? So it's fun to kind of look at a more broad picture. So our focus here is going to be in solar cells, because this is optics for energy. But in a more general sense, there's a lot of various applications you can go. For example, stealth bombers are kind of an application of light trapping, because they like to brag about their special radar-absorbing paint that they put on their planes there. So it's a way of preventing echoes, is all the light that hits it, you want it to stay sucked inside of it and burn it up its heat, rather than create an echo that is detected by the radar receivers. This is an anechoic chamber here. You probably can't see with the lighting really well. But again, the idea is I want to measure the directive pattern of an antenna, so I have to illuminate it with some plane wave, but that's going to create scattering and bouncing and reflections everywhere. And when you're inside a big metal box, that can corrupt your measurement. So what we do is we coat the walls of our chamber here with this special anti-reflective absorbing foam. So any light or radio waves that hit the wall there gets absorbed inside the walls rather than create an echo. So that's where the name comes from, anechoic or non-echoing chamber. So let's talk a little bit about solar energy. This is a really fun graphic you can download from National Renewable Energy Laboratory here. So it just kind of shows the sun's, what does it say? Photovoltaic solar resource. So obviously, not all parts of the U.S. receive the same amount of sunshine throughout the year. So what they've done is they kind of average, you can't really read it, it says annual average solar resource data for, tilt plus latitude collected. So what they've done is say, okay, you imagine a little power meter, you point it up at the sky, and you measure all the energy coming down from the sun, and you average it throughout the year. So obviously some parts of the country are hot and dry, other parts are cold and cloudy, so you're not going to get the same amount of solar influx throughout the year. But this is a fun graphic, as you see New Mexico, Death Valley, Arizona is really hot and bright, whereas obviously Alaska is not so much of a solar resource. So if you live down in Arizona and you want to install solar panels on your roof, you're in a much better situation than if you're up here in upstate Maine, right? So the units here says kilowatt hours per square meter per day, so it's averaged kind of throughout the year. But looking at it, if you kind of integrate this surface, you get essentially like the total energy falling onto the U.S. by the sun. And roughly speaking, if you imagine like a little square like the size of my thumb here, it'd probably be enough to satisfy like the entire energy demand of the United States times 10. So that, I like to always kind of begin by raising the question of, well, why aren't we just flooding the desert with solar cells? If we have the technology right here, there's a picture, there's solar cells from the desert. Why aren't we just supplying the entire country with solar energy right now? Would you care to speculate?
It's not helping very much.
What's not helping?
Government's not helping very much, right?
Why do we need the government? Why don't we just go buy a bunch and throw them out there?
They could like tax it lower, but they help out with the oil industry.
Okay, so economics is what I'm hearing, right?
Yeah.
So that's one of the major reasons. There's also issues with like storage and transmission. For example, if I have a house up here in New York and a solar station here in Arizona, it's a little hard to get energy out there. But that's okay. There's ways to deal with those problems. Maybe they have lots of wind power up here in the Dakotas. But a big problem, like you say, is just economics. It's coal and oil and things are relatively cheap compared to solar cells. So it doesn't quite make economic sense to just buy billions of these things and start pumping them out in the desert. But that story is actually changing. So a really fun fact, right here is where I did my PhD in 2011. And the average cost for a solar installation was about $5 per watt. So that's kind of the big economic metric of solar installation, is that dollars per watt value. So what the industry said way back in like 2009 and 10 is they said, we want to get $1 per watt by 2017, which they haven't quite hit it, but they did a lot of progress. They came very close. We're actually about $2 per watt. 2 or 3. No, 2, right there. So that includes a lot of things. The raw cost of the solar cell. There's also the cost of the installation. There's the tracking and electronics that have to go with it to interface it with the power grid. But overall, it's come down a lot. So that's pretty neat to see over the years, that trend here. So you notice there's also another trend. The bars here show solar photovoltaic installations. And it says annual installed solar PV capacity. So megawatts DC is what they're saying. So you see as the cost comes down, the actual installed capacity is going up. So we're out here in 2017, and it's probably that bar is reaching up there well beyond 15 to 20 or 20,000 megawatts, which is pretty good. Although granted, the total U.S. power demand is like up in the hundreds of gigawatts. So if you were to really draw it to scale of like total photovoltaic power being generated versus total demand, it would be something like this. But that's okay. Give it another 10, 15 years, and we'll probably make a pretty good dent into that. But this is really cool because it means photovoltaics are really starting to become cost effective. So people, if you make it cheap enough, people are just going to voluntarily buy it and install it out of their own economic self-interest. So before we talk about the light trapping issue, it helps to talk a bit about kind of the basic anatomy of the solar cell. You guys even talked about that in this class yet? So you probably actually know more about some of the underlying physics than I do. Because from my perspective, when I do all the modeling, I just want light to come in and get absorbed, and then after that, it's sort of up to you guys to figure out what to do with it. But the basic process, of course, light photons coming in from the sky. You have a PN junction in the semiconductor, and there's all that magic of electrons and holes going on here. When a photon strikes an electron, it excites it to a high energy state, create an electron hole pair, and then they do this little Brownian walk to hit the contacts, and then magic happens and you work. So the big thing we want to do is make sure as many photons from out there are being collected inside here. That's our fundamental engineering problem. Incidentally, it helps to talk a lot about silicon, because there's a lot of different semiconductor materials you could make solar cells out of, but silicon is like by far the big market domination beast right now. So there's actually very important reasons for that. So first off, silicon is very abundant. This is actually a big problem. I don't know if you've talked about cadmium telluride in this class. Does that come up? So it turned out like 5 years ago, cadmium telluride was one of the cheapest ways to make solar cells. But the problem is there like physically isn't enough cad-tel in the Earth's crust to make enough solar cells to actually meet like a large-scale global demand. So it's a nice sort of niche market, and they're probably making lots of money. But in the big grand scheme of things, there just isn't enough of the stuff to go around to really solve all our problems. So we like silicon. There's plenty of it. Like something like 25% of the Earth's crust is some silicate or another. It's non-toxic. So if you were to take this solar cell and just kind of throw it in the trash, it's a lot safer than if you did cadmium telluride, because cadmium is a horrible heavy metal that poisons things. But the Earth's crust already has tons of silicon in it, and it's not really polluting our drinking water that much. So it's not that. That's a big reason why we like silicon as well. It's not nearly as toxic as some of these other heavy metal semiconductors are. It's easier to process comparatively. Just the act of turning it into a solar cell is relatively straightforward. In fact, if you take Mike Scarpola's solar cell class, you'll go make your own solar cell as part of your lab project. Turns out it's just the right band gap, so the efficiency is pretty good. And not at all trivial is the fact that people have been doing things with silicon for the computer chip industry for like the last 80 years. So there's this huge pre-established infrastructure of just mining and processing silicon already. So there's kind of a bias in that sense of we already are really good at working with it, so we're just going to keep on doing that if we can. Otherwise, we have to reinvest another $100 billion into that industry, and nobody wants to do that. So silicon is kind of just the standard for this lecture. Just assume that from now on, every time we talk about solar cells, we're talking about silicon solar cells. So now it helps to talk about the solar resource, solar power perspective. So this is a graph that you get very intimately familiar with if you do a lot of photovoltaic research. So the way you interpret this is you imagine you're floating out in space, somewhere in Earth orbit around the sun, and you point a spectrum analyzer watt meter at the sun, and you just measure the power spectral density coming from the sun. But in any given moment, it's not going to be constant. Like you'll have coronal mass ejections blowing around, you have sunspots. The Earth's orbit is just a smidge eccentric, so maybe in wintertime we're just a smidge closer to the sun than we are in summertime. So the power might increase or decrease by a couple half percentage points. So what they do is they just average all of that stuff out throughout a year, and you get this black spectrum right here. So that's what you see looking out to the sun in space. And if you integrate, so you notice the units here are watts per square meter per nanometer. So if I calculate the area under this whole curve, I get watts per square meter. So then if I have an aperture that's 1 square meter in size, and I collect all the energy to that would be watts. So at 1 square meter aperture, we'll receive 1.366 kilowatts of energy on average when pointed at the sun. Incidentally, just a fun fact, you can superimpose Planck's law of black body radiation right on top of it, and it tracks it pretty well, which is just one of the many ways you can kind of indirectly measure how hot the sun is. And so it's about 5,800 kelvins, turns out. That's what I plotted on top of it. You look at Wikipedia and they say it's 577 something, but close enough, right? So we don't actually live in space. We live on the surface of the Earth, and there's a mountain, an ocean of air above us that the light has to pass through before it actually reaches us. So what you do is you imagine the sun is directly overhead, and I look straight up, and I'm collecting energy from the sun that way. There is, you call it one air mass of air between you and the actual sun. So there's dust in the atmosphere, there's water vapor, there's nitrogen and oxygen, and those ozone. So all those things in the air are going to absorb some of the sunlight as it comes down on you. And that's where you see all these kind of absorption lines here. So that's probably water vapor or something. Maybe that's nitrogen, or who knows. And, so you lose a little bit here, probably just from specular reflection of dust or clouds or who knows. So they call that an air mass 1.0 spectrum. However, the sun isn't ever really directly overhead. we live in the continental United States, and the Earth is tilted. So really, the sun is more about like that angle, right? So the air mass 1.5 means there's 1 atmosphere of air above you this way, and then there's like 1.5 atmospheres at this tilt. So that's where this kind of air mass 1.5 name comes from. And it's kind of regarded as a standard annual average solar spectrum for the average person sitting on the continental US. So there's like a separate standard that they'll use if you're in Europe, but this is kind of like regarded as, this is generally what you see from the sun for the average continental US person. So you notice though, because we're losing a bunch of energy here, we lost a little bit on our total solar resource. So before it was 1.3-ish kilowatts. Now it's almost exactly 1 kilowatt per square meter. What that? So this is kind of our new best friend, this red line here. This is like the standard reference spectrum if you want to, characterize a solar cell. Now, incidentally, so you saw the units were watts per square meter per nanometer. It turns out when you're doing light trapping and dealing with solar cells, that's not the most useful unit. And the reason is because when a photon is captured in a solar cell, you don't just convert all the energy to electricity. You can only get enough energy out of the photon as it takes to excite an electron into the conduction band, from valence to conduction. So there's a band gap effect. So what that means is if I have a very high energy photon, I excite an electron, say, twice the band gap energy, all it does is just fall back down to the band gap again and settle, and all that extra energy gets wasted. So when you're doing light trapping, it makes a lot more sense to say I'm capturing photons, really, and not capturing energy in that sense. So that's why we do a little conversion. This is a new spectrum. It's the same thing, just with a little transformation. So it's photons per second per square meter per nanometer. Okay? So silicon, remember, has a band gap of 1.1 electron volts, so you convert that into a wavelength, which means all these photons out here are completely useless to me, so I might as well just sort of pretend they don't exist. So this is kind of the spectrum we really care about now. All that here, you can't do anything with it, so it may as well not be there. So then, incidentally, every photon with energy above this band gap is not going to give me any actual usable energy. So for all practical purposes, I can say every photon here is going to provide exactly 1.1 eV of energy, even if the photon itself is 2 or 3 times that value. So what you do is you integrate under that assumption, and I get 8.11 watts per square meter. So that is the absolute theoretical maximum power you could in principle get, even if you had absolute perfect absorption and capture with a silicon solar cell. So there's kind of your maximum efficiency right here. So, oh, sorry, I got ahead of myself. So when you throw away this, you get 800 over here. When you do the band gap thing, you lose another like several hundred watts, a couple hundred watts on that. So the total energy is about 488 watts per square meter. That is if you have like perfect thermodynamic efficiency and perfect capture of the energy once you finally collected the electron hole pairs. That is the absolute maximum possible power you could get out of a solar cell. But then, unfortunately, the story is even worse than that, because what you're trying to do is extract energy out of a sort of diode circuit. So what you do is you then do some circuit analysis and try and maximize power transfer to a load. And it turns out you lose even more, and you get about 32%. Is your maximum kind of practical upper limit, or not even practical, it's your physical upper limit to getting energy out of a silicon solar cell with a single p-n junction. So that's called the Shockley-Queisser limit. So this is why solar cells have like very intrinsic upper limits to how efficient they can be. So in practice, it's still a little bit worse than that. So this is a fun little schematic here. This was a paper published in 1999. And when that paper came out, this was the absolute world record holder for solar cell efficiency in a single junction silicon solar cell. And they were able to get 25%. And there's a lot of things, you notice they are kind of pulling out all this stuff. So they use really good high quality silicon here. You notice they've got the surface texturing up here. They, what else do they do? They have a nice 400 micron thickness here. And it comes in these little cells about yay big you can make. And there's a lot of reasons why you still can't quite get that 32%. But this is widely kind of considered about as good as you can do practically. They've probably beaten it since then. This is almost 20 years ago. But if they did, it would barely be like 25.5% or maybe 26. That's the best that I've ever seen. So that's what you can do in a lab. What about what I can buy off the shelf? So earlier this week, I went to Amazon and looked for like high efficiency silicon solar cells. And I found you could buy this guy right now, $1.50 per watt, and it's about 15% efficient. So that's just to give you some scale of the efficiency we get out of these things. So that's what you could do in principle, but it costs an arm and a leg. So if you pull out the stops and go for cheapness rather than raw efficiency, this is about what you get 50%. So just also make sure you pay attention, $1.8 per watt. This value here is a big determinant in how widely adopted this technology is going to be. Yeah.
So does that schematic that you showed at the beginning that shows the amount of energy of the sun in the map of the U.S.
Yeah.
Is that considering these things, like those numbers? Or
that's probably where they get these numbers from, is they actually have like special lamps that are calibrated to that AM 1.5 spectrum. And they take this thing and they stick it underneath and they'll measure its efficiency using that. So in principle, it's rated for 100 watts. But if it's a hot day in Arizona, you might get 120 or 150 out of it. So it's a little hand wavy there, but you have to standardize this stuff somehow. That's kind of, I think, how I understand the rating is concerned for that. So under the average AM 1.5 spectrum, that's how much energy you get out of it. But it could be more. You just shine more light on it. Why wouldn't you just get more energy? You know? Of course, if you're in Alaska and it's cloudy, you're not going to get 100 watts out of that either. So take that number with the grains of salt that it's due. That kind of makes sense? So why do we have low efficiency? What are the main culprits? So the first big culprit we're going to talk about is failure to capture photons. Sometimes light hits it and it just doesn't get captured and it doesn't excite the electron-hole pair and you just lose it. So that's the problem of light trapping we're going to focus on. And it's kind of the first problem you have to consider, because if I'm not trapping the light, it doesn't matter what you do with it beyond that. But after that, there's still layers of reasons or things that can go wrong after the fact. So you create an electron-hole pair, and they do their little Brownian walk, and they eventually get collected at the anode and the cathode. Or they might just recombine somewhere, and you go, oops, I lost that one, right? So there's intrinsic limits to how that's going to work. You also have issues with how you make your circuit. So if you have a lot of extra resistance in your solar cell and you're not matching the impedances properly, you're just not going to extract power out of it that way either. So those are some issues as well. We don't care about them because none of it matters if you can't trap the light. So that's our singular focus today. So why are we losing light? So there's really three reasons I can think of. So the first thing that happens is light. Anytime light hits the dielectric boundary, you get a reflection, specular reflection. So that's reason number one. What could also happen is light will just go through and either fall out the back contact, get absorbed here, or it'll just reflect and bounce back up the top. I don't know if there's really a name for that, so I just call it like transmission loss or something like that. You also have the contacts up on top. They're blocking light, and so the light's going to hit that and scatter away, and you're going to lose some energy that way. So let's kind of deal with them one at a time. So the contacts, you can minimize that. Excuse me. That's why the traces on top of the solar cell are very, very thin. In fact, if we go back a little bit, I think I have a zoomed-in picture. So you see that you have kind of this main trace and this little grid. They're trying very hard to minimize the amount of coverage from that little grid on top of the cell that's just blocking light. That's a kind of inherent upper limit there. You have to keep a reasonably good coverage over the thing, or else, an electron hole pair event over here is going to have to wander over to that contact eventually, and if it's too far away, they just recombine. So you have to have very strong coverage. There's kind of competing factors there. You want to collect your electrons in holes, but you don't want to block the light from getting in. So a lot of smart people have probably figured out that balance as well. So you do your best to just minimize the contact up top. Surface reflections, that you can deal with using anti-reflective coatings. So they're fairly cheap and reasonable, so they're not perfect, but you could get like 90%, 95% transmission, something like that. But that still leaves us with this problem of the transmission loss. So how do I deal with that? I can make my solar cell really thick, which is why that other one's like 400 microns thick, as you saw. So if I just have this thing infinitely thick, eventually that photon's going to get captured sooner or later. But you can't make it too thick, because if it's 9 yards thick, again, those electrons in the holes have to migrate somewhere, so that you can't push that too far. But there's kind of a more important reason why we don't do that, is you have to get pretty thick in order to really capture all the photons. So this is a fun little graph. It shows, it's called the absorption length. So I guess if we go back here, the probability of absorbing a photon over some given distance is exponential in nature. So what you have is kind of this characteristic of absorption length, which is kind of your e to the minus alpha factor there. And that's what this is here. So you imagine e to the minus alpha x kind of parameter, this is your alpha. And you notice as you get very close to the band gap, it approaches 10 microns, 100 microns in thickness. And that's just like your 60% probability. So that means you got to get pretty thick if you really want to capture all of those long wavelength photons. You notice here's gallium arsenide, which also kind of follows the same thing. Fun little graph. But the big problem is silicon ain't cheap. It's cheapish, but if you're going to make it 400 microns thick, it turns out that that's going to add a few dollars per watt to the cost of your solar cell. So that was a big problem 5 years ago, where it was placing like something like 50% of the raw cost of a solar cell. It was just the raw material of silicon that had to go into the wafers. So that was a big push 2 years ago to go thin. So instead of having hundreds of microns thick, let's see if we can make solar cells that are only 1 to 2 microns thick. So now that cost of that raw bulk silicon is cut away from the expense of our solar cell. So this paved the way to what's called thin film solar cells. So instead of hundreds, you see it's about 1 to 2 microns thickness, pretty typical. And I went to Amazon again, and I just sort of looked up thin film solar cells, something like that. And you see this kind of stuff here, made out of amorphous silicon, rated for 136 watts, and it was 6% efficient. But it was cheaper. So just by not using as much silicon, yeah, you sacrifice a lot of efficiency, but it just becomes so cheap, you still come out ahead anyway. So depending on how valuable your real estate is, this can still be a much cheaper alternative. But the problem now is because I'm so thin, I'm not trapping all my photons. So a major reason why this number is so low is I'm not thick enough to capture all the light that hits it. So this is a fun little graphic. Just imagine a plane wave striking a little surface here, and there's no reflections or anything going on. It's just exponentially accumulating. So if you have 500 nanometer light, which is green, so I can put a green here, you notice you absorb like 90% of it, which is great. But when you go out to 800 nanometers or 1,000 and beyond, you're barely even scratching the surface. So all those long wavelength photons are really going to be difficult to capture when your solar cell is very, very thin. So now we're going to do some math and quantify this stuff a little bit more. So remember, this is our spectrum here. This is our photons per second per square meter graph up here. And to put it in perspective, you imagine a 1 micron crystalline silicon solar cell with a perfect electrical conductor as our back contact. We're going to pretend there's no contacts up the front. We're just going to do some raw calculations on how much light can I trap in geometry like this. So when light comes in, you get a little reflection at the top interface, and then it starts bouncing around back and forth. And incidentally, sometimes that bouncing back and forth will either destructively or constructively interfere with that top reflection. So that's where you get all this wiggliness going on here. So sometimes you get a lot of absorption, and that's because this reflection here destructively interfered with the one up there. Or sometimes you get terrible absorption because they constructively interfered. So that's a fun effect. It's called Fabry-Perot resonance, if anyone ever asks you that. But it just is what it is. So you integrate that, and you find that with a little structure like that, I am only absorbing 27% of all the photons I could be absorbing that are available to me from the sun. So how do we do better? So step one, let's put the anti-reflective coating up top. You notice how it kind of smooths out all those resonance effects now. You just have one pass down and then one pass back, and that's it. So incidentally, it increases your light trapping efficiency up to about 40%, which isn't bad. But you notice I still got all this empty territory here left to recover. So finally, we're at the point where this is where I started doing my research in light trapping. This is the fundamental problem of solar cell efficiency we're trying to overcome. So they're cheap, they're very thin, but they're terrible in their efficiency, and we want to make them do better. So the basic idea for light trapping in solar cells says I have maybe 1 micron of thickness this way, but my solar cell maybe that big, or I printed it on a big wide area, so I might have several feet this way to capture my light. So if I can somehow coax photons to go that way, they're just going to go along forever and ever, and eventually they're going to hit something and get captured. So it usually involves putting some kind of obstruction in here that scatters the light every which way, and that extra distance that the light has to travel through to get absorbed, we can call it a path length enhancement. So you imagine, it's 2 microns is like my equivalent path length this way, so 1 micron down, 1 micron back. Or I could scatter a ray maybe 30 degrees, so it'll go 1 down and then maybe 2 or 3 or 4 just by looking at the trigonometry of the situation. So path length enhancement is a term that you'll see thrown around in the literature. So a bunch of smart people did a bunch of math, and they found that kind of the optimal amount of scattering is Lambertian scattering. You guys talked about like Lambertian or specular versus diffuse scattering at all in this class? So specular scattering is what happens on like a flat mirror, where a ray comes in and just bounces perfectly. Diffuse reflection is what happens on, say, this surface here. So it doesn't really matter which way the light hits it just sort of scatters every which way to create sort of this bright white surface. But it's not a mirror the way a perfectly flat surface. So those are kind of like the 2 extremes in scattering when you do optics. So if you imagine absolutely perfect diffuse scattering, you get up to about here, which is an 81% capture of all my available photons. That's in just a 1 micron thickness. So if I were to make it 2 or 3 or 4, that number might go up to 85 or 90. So that's not bad. And this is kind of regarded as like the gold standard for light trapping. So you'll see a lot of papers talk about, the Lambertian limit or the Jablonovich limit, because some guy named Jablonovich is one who kind of published this and figured it out back in the 80s. Or the ergodic limit is another word you'll see. It's not exactly like a hard physical upper limit, but it is kind of regarded as the best you could do practically over a large bandwidth of light. So that's kind of our goal now, is what can we do to achieve that Lambertian limit. So this is kind of sampling of all the goofy papers people were coming out with in the mid-2000s and early 2010. And this is right about the time where I jumped in and started working on my dissertation. And people had some pretty good ideas like that. And one of my favorite was the whole, they call them like surface plasmonics. So people were literally taking their solar cells and sprinkling like gold and silver particles on them and creating these goofy arrays here. And they were sort of reporting like at 650 nanometers, yes, I got an improvement, but they weren't really analyzing the whole spectrum and showing how that would work. And I really like to make fun of them because they're literally just putting metal contacts on top of their solar cell, and which is just blocking light. And you might get slight improvements at this wavelength or that wavelength, but when you average it out over the whole spectrum, it's terrible. It's a dumb idea. You can tell just by looking at it, like, what were you thinking? But it was super popular. Everybody was just publishing on plasmonics and writing all these papers. And so in retrospect, it looks dumb and funny, but at the time, it was like the hot topic. So yeah, this was like the big thing 10 years ago. So to kind of quantify some of this stuff, it helps to think of like idealized models, because it helps build sort of a language and an intuition by which to talk about light trapping and complicated geometry. So there's this really obscure book I found where he came up with this really neat concept called the model N slab. So imagine this big infinite plane or block here, and I'm shining light in it from this direction, and what would normally happen is you get a reflection, then a transmission. Some of it gets absorbed inside, and some falls out the other end. We're going to ignore that reflection. So there's an anti-reflective coating on the top and the bottom. So what you get is a wave comes in, it exponentially attenuates a little bit, and then it flies out the other end. So there's my exponential attenuation factor here, and I can then calculate how much energy is absorbed inside given some thickness. So you'd say the model N slab has an equivalent thickness of 1 W here. So this is 1 micron. It propagated through 1 micron of thickness and is absorbed before falling out the other end. So incidentally, though, we can think about this a little backwards. So instead of saying, here's my slab and here's my thickness and here's some light hitting it, I can say, here is a slab. I absorbed some fraction of my light, and I know what its absorption coefficient is. Now let's solve for its length. And that can be a length I solve for independently of the actual geometry of the thing. So that is called an equivalent path length here. So I'm using this little expression right here. So I know how much light was absorbed. I know the nature of my material, so it must have propagated through that much equivalent thickness. So it's a nice way to kind of intuitively think about, say, this big complicated thing here. A bunch of light comes in, and some of it's absorbed, some of it scatters back out. I can say, okay, well, it propagated through the equivalent of 7 microns at a model N slab. So you'd say that was its equivalent path length. So that's where this idea comes from. So it's just a nice sort of number you can assign to how well you're trapping light. So you can do some math with that, and you solve for some path lengths, and you can do these nice little fun curves. It's a fun little math exercise. I threw it in my dissertation because it was cool. But from there, you can use that to derive kind of the Lambertian limit. And there's this very important result that comes out at the end of the day when you do the math on this. So imagine a very idealized solar cell, so anti-reflective coating on top and bottom, and a bunch of diffuse scattering at each interface. So what happens is some light comes in from the top, it scatters every which way, it hits the bottom, you get some more scattering, and some light falls out, and then just sort of bounces back and forth forever, and eventually some finite amount of energy gets absorbed at the end of the day. So what you do is you just kind of follow the energy step by step. So you start with some random ray of light coming from the sun. It strikes the top, and you get a diffuse scattering event here with no reflections out the top. So you can, turns out the directivity profile for diffuse scattering follows this cosine dependence. So that word cosine scattering might get thrown around from time to time. So that's what you're seeing here. So what we're going to do is just track pretty much each and every ray and add them all up in terms of how much energy gets absorbed in each little contribution. And you get a big, ugly integral in spherical coordinates. So you see you're just sort of tracking the total path length here with its exponential decay, and you're weighing it by the direction it was pointing. So there's a lot more energy going in this direction than in this direction, so that's where that cosine comes from. This is your absorption factor for that particular ray, and this is just the Jacobian spherical coordinates for doing your integral. and you just add them all up. So you go from 0 to 2 pi, or sorry, 0 to pi over 2 this way, and then you integrate again and b through 2 pi. So you're just adding up all the rays and how much energy was absorbed, and that's your total absorption for this one pass right here. Then we do, so that's actually a really difficult integral. So you do some approximations on it. So in the thin film world, we are going to assume that I have a relatively low loss material, because you saw the path, the absorption like in silicon is like several hundred microns, and they're very, very thin. So this number we're going to assume is very, very small. So it has a small absorption coefficient over a small distance means a small number. So you do a little Taylor series approximation here, and you wave your hands at the math a little bit, and all of a sudden you get a nice approximate answer to that integral. Or you could just do it in a numerical calculation too, but we want to do kind of a very idealized approximation. So you actually get a very simple 2 alpha W for that first pass. So then when the ray strikes the bottom, some fraction of energy falls out, and another fraction scatters back in. So you do some basic optics, some Snell's law approximations, and so you have your escape cone issue here, and you have what's called a light extraction efficiency. So some fraction of the light hit here and escape, and the other reflected. So maybe you lose like 5% of your light here, the other 95 reflects, and that depends strongly on the index of refraction. So that is the fraction of the light that leaves the bottom, and the remainder just bounces back up and repeats. So I'm solving for the reflected energy. So I have the fraction of the energy that arrives at the bottom, and a little bit leaves, and the rest is reflected. So that's what that's telling you here. You then kind of wave your hands at it, because everything's approximate. So you get basically that. And what you do then is you repeat forever. So you do a summation of that over an infinite number of bounces, and that's the total amount of energy absorbed in this Lambertian surface. And you actually get a nice simple result, 2 alpha n squared W. Not bad. So it's a little hand wavy, but it's approximately valid, so why not? And then what you do is say, okay, well, let's throw away the bottom here and put a perfect scatterer here instead. And what that basically does is it doubles your absorption factor there. And then when you go back and you solve for the equivalent path length, which is that thing you saw 10 slides ago, you get this 4n squared W. So the whole point of all of that is if you have perfect Lambertian scattering inside your solar cell, it will behave as if it is 4n squared times thicker than it really is. So the index of refraction for silicon, incidentally, is 3.5. So you square that times 4, and you get roughly 50. So what all that means at the end of the day is, in principle, if I have 1 micron thickness of a silicon solar cell, and I work all my internal magic just right, it will behave as if it's 50 times thicker than that. So they call it, sometimes you'll see the 4n squared limit for silicon solar cell trapping, that kind of thing. So it's a 50 times path length enhancement. So if you ever get involved in light trapping in solar cells, this is a big, big deal, and you'll see it all over the place. So now that's kind of the technical fun part of the lecture. Now we're going to take a step back and say, well, can we cheat it somehow? So this is a fun little thought experiment I like to give. And it says, okay, let's imagine I have a solar cell. Again, maybe very thin, 1 micron, but I'm just going to coat it with aluminum and put little spots here with anti-reflective coating. And I'm going to have a big lens up here where light comes in, and I focus it to this tiny little spot. So you look at that and you think, wow, that's basically like perfect trapping, isn't it? So in theory, if I make this really tiny and a really big lens, I can get almost perfect light trapping here. So, and the reason why I really like this thought experiment is it reminds me of when I was working at this startup company a while ago. My boss would always come to me with crazy, wacky ideas that are kind of like this. And your job as an engineer is to either say, yes, we can do that, or no, that's a terrible, stupid idea. You should be ashamed for having thought of it. So this is one of those fun questions where, in principle, you could do this, but do you really want to? So any thoughts on that? It seems like it should work. What might be some trade-offs there?
Heat problem?
Heat?
Yeah. From focusing the light?
Yes, yeah. If you focus a lot of light, you're going to heat up the solar cell a little bit, and they do lose some efficiency that way. And if I'm concentrating like 3 kilowatts onto a little space, I might burst my solar cell into flames. So maybe let's say I just don't overdo it, or I'm doing this in Alaska where it's not super hot, right? What if I do that? Here's a fun question. What if the sun is a little to the left? What'll happen? Yeah. So if I'm not perfectly aligned, you see that. So that's one of your first major problems is you have to track the sun if you're going to do something like this. And if you misalign, oops, you just lost all your energy. So it's kind of sensitive to the alignment there. Incidentally, so that Lambertian limit you saw, it only applies to like random diffuse light from all over the place. If I have focused light, you can in principle trap better using something like this. But what about just like these big giant props and lenses? How much do you think that stuff costs? How much do you think it costs to create a big tracker that follows the sun? And remember, I need $1 per watt. So if I'm at $1.20 per watt with a solar cell already, and I put this contraption on top of it, how much am I going to add in cost and expense, you think? Remember the benchmarks, let's go way back here. So this guy is $1.20 per watt at 6%. And this guy over here is $1.80 per watt. So even if I doubled my efficiency, if I cost any more than 60 cents per watt to put that stuff on there, I still don't come out ahead because this is almost 3 times the efficiency. So I'd have to triple the efficiency at less than a 50% increase in cost. So that's one of the big sort of problems with this sort of thinking. Another interesting fact, so we have to track the sun. It's expensive and bulky, and if I misalign at all, I lose a bunch of my efficiency. But let's not forget, I'm already trapping 81% of the light with 1 micron here. So the question is, let's suppose we go back here, and I'm doing this absolutely perfectly. I'm trapping 100% of all the light onto the solar cell. How much efficiency improvement would I get from that? 25%. I went from 80 to 100. So if originally this thing was 10% efficient, and I put this thing on here, I could get to 12%. So if it adds any more than 10% to your cost, it's not working. I'm already trapping 90%. Or what if I just doubled my thickness here? Right? And why would then that 81 suddenly becomes 89, right? Or maybe it becomes 90. So I could get a huge boost in my efficiency for other ways. So that's why I really like that thought experiment. It's one of those things where just because it could be done doesn't make it a good idea. And there's other ways to get what you want without big, complicated structures. Okay, so that's the end of our lecture on light trapping. You're all experts now. If you have any questions, now's the time.
So did you come up with that orange grid thing?
No, some dude back in the 80s figured that out. What I wish I could claim credit for was actually doing an intuitive derivation for it. Because you'll see the derivations and justification for it were these weird obtuse arguments based on thermodynamics and densities of states, where it's no, just follow the light and add it up. So that's really the only difference for this lecture here. But I wish I thought it up, because everybody cites that guy. He has 100 citations to him in Spanish, so. Another question? Yeah?
I was just at a seminar. There's a lab seminar in California.
Mm-hmm.
We take all the metals and blindfold and mix all of those solutions and test them as a solar panel.
Uh-huh.
What's the logic there? What is the
So let's
thousands and thousands of tests.
see. Let's go back to. Oh, wait. There we go. So would probably have to do with this. So silicon is fairly expensive, but it's a nice kind of gold standard for solar cells right now. But what you want to make is a semiconductor with a band gap somewhere around here. But in principle, if you happen to come up with a good semiconductor with just the right band gap, and maybe it's cheaper to produce, then you could stop using silicon and use this stuff instead. Or maybe it's just easier to process and work with than the silicon, so you save a lot of money that way. But it won't really have any fundamental effect on the efficiency. It'll be more of a practical issue with the materials availability and the cost of manufacturing. But I know that was kind of a mad scramble, in my opinion, to go through. People, silicon was just everywhere, but it was expensive, and there were concerns where there were other materials that made better, more efficient solar cells, but there wasn't enough material in the Earth's crust to actually make enough of it, and so a lot of people were just playing around with, ooh, I can make a solar cell out of this stuff here, or I can mix these materials here and make a semiconductor. Now I've got a solar cell. So you dig around, you'll see people making solar cells out of everything. So Mike Scarpola's group, he does CZTS, so it's copper, zinc, tin sulfide. So those are very plentiful materials that in principle are cheap and easy to work with, and he's trying to make fancy solar cells out of that because maybe it's cheaper than silicon, and it's abundant, non-toxic, and you could maybe kill the solar cell market that way. So that's what they're doing. Okay, and thanks for stopping in. You all learned something. There you go. So you're going to post those online.